Okay, welcome back. So we now move on to part 3. It's still, I think the part 2 has laid a good foundation in terms of modeling framework, because in a way the part 3 models are still in the family of mixed effects hierarchical linear models, although they are specifically tailored to modeling data that fall in the realm of research design 3. And so here's the plan where we talk about this new, a different kind of research design called accelerate longitudinal cohort panels data. We'll look at the data structure, characteristics, and examples. And then we'll fit the hierarchical linear model, growth curve model specifically to these data to test, I situate this model more or less in the sociological theories of aging called the principle of cohort differences in aging. And then some basic model specifications you can use to test it, and then using the empirical applications of depression and disability, using a locally housed, one of my favorite data sets in social science, of all time, Americans Changing Lives study. So the data structure, it's called Accelerate Longitudinal Panel, mainly in reference that it's different from single cohort study because it follows multiple cohorts forward over multiple points in time. And this is an important advance in aging and cohort research because the name comes, because it allows a more rapid accumulation of information on age for multiple cohorts than does a single longitudinal cohort design, and hence accelerated. So this shows an example of this data structure that follows 4 birth cohorts, 1, 2, 3, 4, forward in time in 4 waves, 1, 2, 3, 4. And so this kind of design is especially so first and foremost, the difference from the first 2 designs is that these are true cohort data with cross-time linkages within individuals. So they're not synthetic, they're actual birth cohorts. The second is that it also is a kind of multi-level data in the sense that there are repeated observations over time at level 1 or nested within individuals at level 2. While you can conceivably add more levels if you want to consider even higher levels than individuals. It's like I said, a very flexible modeling framework. This kind of data is particularly useful for testing aging-related hypotheses within a cohort-specific context. And then, so because it allows for, the distinction between intra-individual change within cohorts across columns, the horizontal line, under age pointing to the right, and which is different from inter-individual change, inter-individual differences across cohorts, across rows, which is this vertical lines. So this is a very sort of promising kinds of data that we could use for that. And also with more waves of data collection, we have longer age trajectories forward in time, which will contribute to less confounding of age and cohort variables. So the example here I will draw from is from the ACLs, where we use the data from the full age range that can be classified into 7 birth cohorts. I'm only using the first 4 waves. I know that the ACLs keep collecting data, and I have 7 waves altogether. But at the time the analysis were done, I used the first 4 waves. And so this is an example from the ACL data that follow the accelerate longitudinal data design. The data are from depressive symptoms measured by CSC scales. And this is the age, a truncated crosstab of age by cohort, where we have 6 10-year cohorts and ages 25 to 95, where you can see how at each follow-up, respondents in each cohort aged in together that gives cohort-specific age trajectories that follow exactly the same shape that I showed earlier, except for it is transposed. Doesn't matter which, direction. So this is, the kind of data we're dealing with. So a few words about, the theoretical background. So Matilda Riley, in her presidential speech at the 1987 annual meetings of American Sociological Association, put out this famous sort of principle of cohort differences in aging theory that emphasizes distinct aging experiences, across different historical cohorts. So that that sort of has framed the research that think about aging at that time. Interestingly, the principle was not frequently or well tested at the time. Well, in 1980s, there were probably not that enough data. Our Jim House here also has also been a sort of a pioneer scientist that advanced a lot of theories on social stratification of aging, such as cumulative advantage and disadvantage theory that hypothesized, increasing social disparities with age, whereas age as leveler hypothesis predicts the opposite, which is the decreasing social disparities with age. So that clearly has brought a within cohort perspective, even though it was not made explicitly so. And the empirical tests of these hypotheses have yielded highly inconsistent mixed evidence for a problem that I will talk about in the next slide, because these two theories need to be taken together simultaneously in order to conduct proper tests. So and testing these hypotheses would require addressing some fundamental questions concerning the distinct aging experiences across cohorts. So the first question is, are age trajectories different across birth cohorts, which I term as intercohort change hypothesis? That essentially, tests the first principle. And second, do differences in age trajectories within birth cohort, aka social disparities, vary across birth cohorts? So I term this as intercohort variation in intracohort heterogeneity hypothesis. So if you put this test of social stratification of aging in a cohort context, you have to answer the second question, or essentially you're addressing the second question. So the reason why empirical studies have given inconsistent or mixed evidence has to do with a major issue with longitudinal analysis of change. And that is the confounding of aging and cohort effects. And so I will then talk about the models that help to address that, called HAPC growth curve models. So the general analytic framework for addressing this issue actually was first proposed by sociologists and psychometrician in combination by Miyazaki and Roundenbush in an article published in Psychological Methods that talk about how you can use this model to disentangle the effects of aging in cohort. So we'll introduce this model specification for testing various aging and cohort-related hypotheses. So I made this summary table of the kind of things you need to include when testing each hypothesis. So first, the intercohort change hypothesis, you're essentially testing differences in the mean controlling for cohort, or cohort differences in the intercept and mean, as well as cohort differences in the rate of change with age, which essentially is age by cohort interaction effect. And so, an intermediate step is that when controlling for cohort, you can better assess intracohort heterogeneity by adding to the first model the group indicators, sex, race, SES, and such, to both the models for mean and intercept. And then finally, the intercohort variation in intracohort heterogeneity, you add in the final model the cohort by group interactions to both the model for mean and the model for linear rate of change. And this final model is the most full and saturated model that can sometimes be quite reduced in actual practice. So the model specification for testing the first intercohort change hypothesis, which is the foundation of all hypotheses, It's at level 1, repeated observation model within individual model is, specified as such. So it's, suppose y is the response for individual I at time t is a function of age and age square. So we have a quadratic age trajectories in this example, where beta 0k 0I is the intercept at the 0 value of all predictors. In this case, if we center age, it will be intercept or expected mean at the center, which is cohort median age. We'll talk about in the next minute. And then beta 1 and beta 2 are the growth rate parameters, linear and quadratic growth rate. So the level 2 individual level model will take the intercept and linear growth rate to be the outcome and model them as functions of cohort, right? And so for equation 2, we add cohort to intercept. Z is a vector of other individual level covariates that you hypothesize to be related to the outcome. And for the linear growth rate, you could do the same. Here is a reduced model. I'm interested in cohort variation in the rate of change. And so the interpretation of these model parameter, then gamma 00, of course, is still the mean. Gamma 01 is the cohort effect, which is the mean difference between cohorts. And for the linear growth rate, gamma 10 is age effect, right? It's the expected linear rate of change in the reference cohort, where gamma 11 is the age by cohort interaction effect, which means the mean differences in the rate of change between cohorts. And so you could do the same for the quadratic growth rate here, but I omitted them here, but it can be theoretically added. And then you come up with this combined model where similarly what you have is the first part is the fixed effects of the individual and within individual level covariates. And the second part is the random effects part. Although in this case, we're less interested in the random variance, but more interested in a fixed effects estimate. Now, the use of growth curve models for cohort analysis is complicated by two issues. First, because the observable age categories of different cohorts initiate and end at different ages, if you recall the diagram that I showed earlier. So the cohort comparisons of age trajectories are based on different segments of cohort members' life course. So when the observations of one cohort are not overlapping with another in age, one cannot compare cohorts at the same ages. In this case, age and cohort are difficult to distinguish because earlier cohorts are older in age. So this raises the question of potential confounding of age and cohort effects. So two analytic strategies can be used to resolve this problem. The first is using centered age variable. Here, particularly if we center around median age of each cohort, so the centered value then is not correlated with cohort membership. So this helps to prevent bias associated with systematic variation in mean age across cohort, and also minimizes the correlation between age and age square and stabilize the estimation procedure. That's a pretty good tip to have. And second is that it has to do with better data. So data collection is important. With accumulation of additional waves of follow-ups, so the number of overlapping ages of adjacent cohorts increases, so which then increases statistical power. In this case, age and cohort will become less and less confounded, making it increasingly possible to compare cohort differences in age trajectories. So this is the one issue. The second issue concerns period effects. You may be wondering, where's the period effect? Now, the models specified above do not explicitly incorporate a period effect variable for both substantive and methodological reasons. First, in contrast to the synthetic cohort design that usually covers several decades easily, accelerated longitudinal survey data are very costly to collect. It's spent a long time following actual cohorts. So they typically span much shorter time periods, a decade or so, with the exception of ACL, of course. So the effects of period in this case can oftentimes be assumed to be trivial and omitted from the models, especially if the theoretical focus is on aging. It's unsatisfactory, right? Because you basically have to be lucky. So second, it is, there has to be some methodological way to take care of this issue. So second, if we are to, estimate a separate period effect, it's challenging to do so in the framework of the hierarchical growth curve models for longitudinal data. Because within individuals, age and time period or survey waves are exactly the same time index variable. So in growth curve models, you pick one time index variable. It's either the wave or the age, but not both. So in this case, age and period are completely collinear. So one can, in this case, focus on the age by cohort interaction effects. Just the same logic as cohort can be interpreted as age by period interaction. So the reason why you could do this is that because cohorts vary in age at any historical moment. So effects associated with historical time, if any, tend to produce cohort differences in the age outcome relationship, aka age by cohort interaction. So this is a good way to capture the period effects or account for it in this framework. Of course, alternatively, you can estimate a CCREM to explicitly control for period effects, although you'll have to make the assumption of independent observations within individuals over time in this case. So here are the SAS sample codes for the ACL depression data, where you should be relatively familiar by now, where you have the same model and random statement for the fixed effects and random effects part. And then this data is XT mixed command, where you specify just the same as an example. So here are the some summaries of the model results for the CESD outcome to measure depression, and also I have included an additional outcome of physical disability from the ACL data. So this table summarizes the results of the model estimation. I separated out the intercept, the linear, and quadratic growth rate. Just for conceptual alliance, you can express it in different ways using a combined model specification as well. And so you could see, is there support for the intercohort change hypothesis? You can see this from significant cohort variation in the intercept as well as the growth rates, right, for both the depression and disability outcomes here, which suggests a strong cohort, significant cohort variation in age trajectories of depression and disability in both cases. And here are the model estimated or predicted age trajectories of depression on the left and disability on the right, where these can come from the model estimates I just showed in this table here. And so we can see how more recent cohorts have higher levels of depression, but lower rates at the same ages compared to the previous cohorts. And they also have lower rates of disability, but somehow steeper rates have increased with age compared to their predecessors. So very cohort-specific age trajectories for both mental and physical health in this case. Now, if we move on to test a more complicated intercohort variation and intracohort heterogeneity hypothesis, the level 1 model stays the same. It's repeated observation, so only age is the indicator there. For level 2, individual level model, we have for the intercept, we include individual level covariates, including cohort, sex, race, and here we include cohort by sex interaction and cohort by race interaction, which help us assess cohort differences in sex and race gaps in the mean of the estimated health outcome. So the corresponding interpretation of the model parameters are given here in case you get disoriented in terms of what am I looking at, what am I estimating. And so gamma 0, 1 continue to be the cohort effects in the mean, gamma 0, 2 and 0, 3 corresponding to sex and race differences in the mean, and gamma 4 and 5 are the cohort differences in sex effect and cohort differences in race effect, respectively. So And then level 2, for the linear growth rate model, you could test exactly the same, and how the cohorts also differ in the age effect in the linear rate of change by plugging in the same variable. Now here, because it's beta 1i is the age coefficient, so any any variable you plug in this equation would result in interaction with age. Okay, so while gamma 1 is the same as we saw before as the age by cohort interaction, the rest of the terms will give you two-way and three-way interactions. In practice, I oftentimes find if you include all pairs of two-way interactions, the three-way interactions will drop out. They tend not to be also significant on top of the combination of their two-way interactions. So, but this is the theoretical full model. And then you get to, appreciate the interpretation of these parameters. It's very tedious, but it's like a dictionary. You don't have to remember it. You can go back to it and look for what it means if you plug them in the model. So once you have the model, you can write out the codes. So it's always follow this step, go step by step through the model estimation. And then here are the updated results where I also look at the cohort differences in the group heterogeneity within cohort by plugging in these additional interaction terms. And so here are the updated results for depression and disability respectively, where you find both sex and race differences in the mean vary significantly by cohort in mental and physical health. And then for the linear growth rate, the only thing that turns out to be significant, all the three-way interactions drop out, by the way. So, but this age by cohort interaction and age by sex interaction for depression remain to be significant, which I will show next in the graphics what they look like. So this is the predicted mean health outcomes across cohorts estimated by the model. On the left is the CSD outcome, on the right is disability. So because we did see sex and race differences that vary by cohort in the mean, and this is what the graph correspondingly show, where female and women in more recent cohorts suffer from higher mean levels of depression than men, and the gaps increase over cohorts, across cohorts. And physical disability, men and women, females tend to have higher physical disability, but in more recent cohorts, these differences converge or decrease a little bit. There are also substantial race differences in CSD, which I don't show here, but that's predicted in the model, and you should expect to find the same if you fit the data. And here is the predicted age trajectories. I'm sorry, I keep pushing the wrong button. Of depression that shows how that further support the hypothesis of intracohort variation and intracohort heterogeneity, in this case by sex for mental health, because it means that within cohort sex gap does not uniformly increase or decrease across the life course, but varies by cohort. So such that for some cohorts, even for the earliest cohorts, older men had higher mean and trajectories of depression than females, whereas more recent cohorts, females disadvantage increase, and then they either crossover pattern or parallel or converging patterns. So the shape of the sex gaps in life course trajectories of CSD vary highly across birth cohorts in this case. So here are what you can do with these models and fit to this data. This is just an example. I believe there are many other kinds of group differences you would like to examine, such as by SCS or any other kinds of characteristic. But just to summarize, I think it's suffice to say here that cohort change is important for theory, measurement, as well as analysis of aging and social inequalities over the life course. It's not a good idea to omit it. It's a good idea to test it. And so because we have seen evidence from a strong study using excellent data from ACL, for example, that cohort effects strongly condition overall health trajectory, such as the trajectories of mental and physical health differ by cohorts, but also cohort effects, by including it, can modify our existing explanations of social disparities in health trajectories. Depending on the cohorts for which you have data, you might draw completely different conclusions with regard to the evidence for cumulative advantage versus disadvantage, or age as leveler, or constant, persistent social inequalities with age. So it matters. I think I've just zipped through it with, really fast talking, but I'd stop in this slide that provide additional key references and see what questions you might have. Yes, please.
Is the issue with model specification for the period effects, is it an issue because they're growth curve models, or because of like the longitudinal, call it accelerated longitudinal panel studies? Like, I guess, where is the issue coming from when it comes to the period effects, if that makes sense?
Yeah, it's a combination of both. Let me, I could go to all this. Yeah. Right, so the data structure is such that you follow actual growth cohorts forward over time in each wave. So at each wave, the individuals have a recorded age, right? So within individual, age and time are the same variable. Now, in the growth curve file specification, so in this case, the repeated observation within individuals, you need to put in an indicator of time. In this case, I put in age. Alternatively, one can use wave or survey year. You cannot put both age and wave in this equation, because within individual, you have repeated observation. Depending on how you express that repeated observation, you have to pick up age or time. So there's no inclusion of a separate period effect in this case, and we address it with this guy, gamma 11, through the change of rates between cohorts. Yes, great question. Any other, Paul?
This is one from the chat. Could this same analysis be done for estimating medians instead of means?
Yes, absolutely. So I adopted the initial methodology by Miyazaki and Roundenbush, where they did the exercise by picking a midpoint. If I could go back to the data structure, right here. By median, they mean, for those of you on Zoom, I'm sorry, I am moving away, and for the live audience, this is where it matters to be in person. So for instance, for the most recent cohort 6, you find somewhere in the middle, this is what they loosely call median cohort age, let's say at age 35, and you center the age around 35 for this cohort's, pick a middle. You can technically do the distributional median or the distributional mean. It does not matter, so long as somewhere, some measure of central tendency, somewhere in the middle, by which you can center the variable. So the purpose, the exact numerical value does not matter. What matters is that when doing the centering, you remove the correlation between age and cohort order, right? So either way is fine. Yeah, but I think finding the middle point seems to be numerically easier. But you can easily compute the mean as well. Doesn't matter. Any other questions? The examples come from these articles, and the data were described by Jim House in his introduction of the data as of 2002. I saw another question came up, or So for the question for the last part, if there's no other question for this section, I could definitely pick up that because we have a little time left.
Can you hear me?
Yes, you're coming through.
Is it okay to ask?
Yep, go ahead.
So, first of all, Dr. Yang, I was a grad student at the University of Chicago while you were still there, and yeah, your success and career brings humility and courage to all of us. So, thank you for that. My question, I'm sorry if this is like embarrassingly basic, but I'm still very hung up on the whole like setting of all of this within the random effect structure. And it might be that there's just like a misunderstanding that I have about how these models work. My understanding, and you kind of addressed this earlier, is that let's say, for instance, that you're interested in how education structures things like obesity at the level of means and the overall means, and at the level of age and level of period and level of cohort. And your model sets it up with like age, period, and cohort, and then you've got a results afterwards that are looking at like, you know, hey, how does, let's say, education correlate with age levels and period levels and cohort levels of obesity? But there was something you said before when I asked about like, well, don't these models just assume all of these effects are uncorrelated with each other, that I really wanted to get clarity on. And it's that the assumption is that they're all uncorrelated with each other, but don't the models impose them being uncorrelated with each other as a constraint? So if you have education as a control in like the body of your model, or as a covariate in the body of your model, the model cannot, by definition, show you any correlation between education and the cohort effects and the period effects. Or is it the case that the model is like computationally, mechanically, what have you, it's just kind of assuming that, but actually you still reserve the ability to check whether or not that assumption is like empirically the case, or is it just as opposed to it just being a constraint put on the model itself by the software?
Okay. Thank you, first of all, James. Is that your first name? Yeah, thank you for bringing the University of Chicago lineage. I relish those formative years of my career, and I, basically met the best students and scholars at that university. You included, I think, of my career. So I really appreciate your bringing that up. And I also, I could tell how deeply entrenched you have been in various advanced statistical methods from your question. I can clarify that in several ways. First and foremost, this is an abbreviated example of the model specification. One always, and I always did, start from the simplest model possible to fit any data before I actually start testing explanatory hypotheses. In this particular example, the very first model to fit is a basic random intercept model with no covariates in, which basically means if you're looking at equation 3 or 2 here, can you see the screen? Or equation
Yes.
1, we start with a model with beta 0 JK, which is just the intercept, meaning that JK means period and cohort specific variance with no individual level covariates whatsoever. And then at level 2, we have the same equation, which is the random intercept that specifies random cohort and period variance around the mean. All right, so this is always the first model to start to sort of test the multi-level level 1 and level 2 heterogeneity through the specification of error terms. And then stepwise, we add the age effect in this case, and I didn't come up with H squared just you know, by guessing, because, you know, by a lot of exploratory and descriptive and also supplementary analysis to come up with this. So this is a result of multiple stages of model fitting. I just did not specify this at the outset. So I did find quadratic age effects here. And then comes adding other, you know, covariates that I wanted to test based on the literature, including sex, race, education, and income. So it's, I don't think it's an imposition of the sort that you just mentioned in the absence of, you know, especially in the absence of all the covariates. Especially if you look at beta 0 JK, where it's explicitly testing the J and K, where it talks about the variance by J, cohort J, and period variance by cohort, period variance class K periods, right? So this is explicitly expressing the error structure at the two levels by not imposing anything on the level 1 covariates. And even adding covariates through the specification. So if you look at the subscript of age, sex, race, and education, they're all specific to IJK, meaning that they're for individual I, for cohort J and period K. One can easily also test the variance of any individual covariate, you know, that's listed here through their parameters beta. Here, I'm testing a simple intercept model, so that's why beta 1, 2, 3, 4, 5, 6 are fixed, meaning they don't have JK subscript, meaning that I'm not testing their variance by J and K, but I can, as I later did, with the random coefficient model. I'm scrolling through here. It's, as you can see, for example, I'm not testing education, but I did before. So in this example, I'm focusing on sex and race, where their coefficient now have the subscript J and K, where I test their variance by cohort J and period K. All right, so this is a direct test of independence. If you do not have, which I did also for education, by the way, if you're interested in education per se, I somehow did not find a significant period or cohort variance for education parameter beta 5. And that's why I'm not writing out beta 5 as beta 5 JK, specifying it to have CMP error, you know, variance in it as the residual, as I did for sex and race here, because I already did preliminary analysis suggesting that there's no J and K specific variance in the effective education beta 5. So this is an explicit test of independence, as you just were talking about. So I'm not imposing this education to have fixed the beta 5, but I also did test the beta 5, whether beta 5 have variance, you know, do significantly vary by either J or K or simultaneously by J or K. So I do not think that it's an imposition of the model for, you know, education to be independent of, you know, period and cohort, because I did, you know, you could use this model to explicitly test that, as I did here for sex and race, which here, you know, sex and race do not show up to be independent, right? They do not show up to be independent of C and P, you know, because of the variance components do show up to be significant for these coefficients.
This is helpful, and I think that my basic misunderstanding was that you're essentially like that it was fitting the random slope rather than the random intercept, and I apologize for that. The next question I had, though, if that's okay, is so then how would, like, I know that you've done quite a bit on like variance components and like heteroscedastic regression as well. Like, let's say that I specifically wanted to see how the variance at the level of period and the level of cohort was determined by education, and the variance of age was determined by determined by education. Like, that, does that get me into more thorny territory? Because then essentially I'm modeling the decomposed error terms, and those do have assumptions about being uncorrelated with predictors in the main part of the model.
I don't think so. Not that I could recall. I'm not entirely sure of the nature of the question, although I could assure you that conjuncting this HAPC model with the heteroscedastic, like VCR, I cannot say that word without being stumbled.
Me neither.
That regression can help to, simultaneously assess both the between group and the dispersion. With regard to whether the dispersion can be can be specified as functions of other covariates that could be correlated with each other, I did not explore that explicitly, but I don't expect it to be anything beyond the framework of heteroscedastic regression itself.
Okay,
Yeah, great question.
that is
Thank
super
you.
helpful to me. Thank you so very much. And yeah, wonderful seminar so far. Thank you. Looking forward to the last hour.
Thank you very much, James, for your great questions. I would take a short break. I think we're running out of time, but 3 minutes break. I really want to get to the end, which I think is the very best. So bear with me. get the things a little bit better. The good news for the last part, there's no equation. That's of course based on the fact that you've had enough, earlier. So it's not like a real relief or something, but it's a little different. So this part, I hope everybody's back here. So we're getting started with the last section. To me, this is where sort of, my current active research is, taking place. I'm super, excited to share with you, my probably changing on a daily basis kind of view on this. But lo and behold, I'm still like overall very positive and excited about it. So what this part is doing is building on the last part pretty tightly, but it's taking it to a messy or big data kind of level. So longitudinal integrative data analysis, or IDA, for research design 4. So I will talk about what this design is like. What does it mean and what does it take, and some resources you could take away to build your own. Based on my past 3 years of struggle. And then I will talk about the general guidelines and framework for longitudinal IDA using this kind of design, using the example of recent studies of BMI and cognitive aging. And so here, this looks familiar. So what I'm trying to show is that this is an extensive life course longitudinal design that consists of that combines multiple accelerated cohort panels that we just talked about in design 3. So in a way, it's augmented research design 3. It's a mega design 3. So an example of this data structure is shown here. Again, on the left for study 1 is the similar kind of, following 4 cohorts for 4 points in time, age range between 15 and 45, so adolescents to midlife. The second study actually follows exactly the same structure, except for that it covers different range of birth cohorts and slightly older age ranges, right? So what I mean by applying this extensive life course design is to use what's called the synthesized cohort sequential design to construct a pooled data set that combines the 2 data sets combines these 2 studies by overlapping ages, as indicated by the grayed cells here in the middle. So what this means is that this design augments the consisting accelerated longitudinal panel study, from each individual data set with increased age range. Now the age range goes from 15 to 55, and then increase the cohort coverage also for now we have 5 cohorts altogether. And also what's increased is the sample size within these gray cells that are overlapping across these 2 studies. So this is, a newest development of, kind of expansive life course studies that particularly happen a lot more often in studies of aging. And so the key characteristic, I find it easier to draw examples in this case because there's no, other than the generic diagram that I just showed, I think it's more interesting to apply it to a real study. So this comes from my most recent study of cognitive aging. It has interesting graph my students helped to put together. I really thank them for this visualization. So this is an example of integrated data from multiple national population-based cohort panels, including AdHealth, Adolescent and Adult Health Project, HRS, which we're familiar with here, and MIDAS, Midlife Development in the United States, and ACL, Americans Changing Life Study, we just looked at. And so they collectively cover almost the full life course from adolescence to old age. And so hence extensive life course design. And it also combines multiple birth cohorts with substantial age overlaps, especially if you look at them together in this way. And then it also ends up giving you, when polled, a massive sample size. In this example, we have over 60,000 individuals followed over 25 years. And so creating the integrated data set is the most difficult step of all. And my team has, using NIH grant recently, we did upload some public use source codes on the project website where you could put together these 4 data sets for any analysis you would like to do for any variables that these data sets have. So I think it's a very useful resource for you to access if you are interested in this type of studies. And so the analytic method is called IDA, where it's a methodology for analyzing the originating psychometrics again. It's methodology for analyzing 2 or more independent samples simultaneously. There's a what's I called strong form of IDA, where it's also pooled IDA, where you combine data sets from separate samples using the cohort sequential design, which is what I just showed in the diagram. There's also a weaker, a moderate form of IDA where it's called coordinated IDA, that where you fit parallel models to each separate sample. And the results are compared within and across studies qualitatively. So longitudinal IDA is a novel application of IDA to longitudinal modeling of age trajectories. Now, we can use the pooled IDA based on the new research design 4, or, in cases where measures are difficult to synchronize, harmonize, we also have the option of conducting coordinated IDA based on research design 3. So I would like to highlight some innovative advantages despite the massive amount of data work and preparation. So if you know the prize, you'd probably be more motivated to go for it, right? So I think it's terrific because it offers the possibility of testing novel life course hypotheses over far more extended developmental and historical periods than any single study can allow. And also has increased power. This is very attractive because when you have larger combined sample sizes, you have greater representations of diverse populations. It can help to address a lot of interesting questions of, in your own studies. And then it also strengthens inference a lot, especially when you have longer age trajectories across more birth cohorts. As I said earlier, that this, it's an improvement of data form and collection that help to decrease the confounding of age and cohort effects very effectively. And also, this methodology has the advantage of allowing you to model heterogeneity across studies explicitly, which helps to strengthen internal and external validity across, about population inferences. And lastly, so it's kind of an NIH priority, to be able to support data sharing to arrive at a more cumulative science of population health. So it's very desirable from these perspectives. Now, the difficult part here, after putting the data together, is how on earth do I account for study heterogeneity? Now, there are several principles you need to consider and draw on existing methods to deal with. First is the measures. This involves constructing harmonized and commensurate variables across studies and across waves. And the second, sampling design varies a lot across studies. So within the modeling framework, you can model study membership as fixed effects with added tests of study by cohort interactions to deal with this very succinctly. And then also historical time. This is sort of the topic of the day, right? So you could use what we have just talked about to model cohort and period differences by age by cohort interactions. And you can also add fixed effects of study membership because studies take place in different historical time periods. Controlling for study membership adjusts for that effect pretty precisely, as you can also build in cohort by study interactions to make it more rigorous. All these things you could do to adjust for the effects of time. And so longitudinal IDA then, it's vast in scope and kinds of choices you can make. So I will just showcase 2 recent studies that use different forms of IDA to do interesting analysis. The first one is the using the growth curve models to, for pooled IDA of research design 4 using BMI data across these 4 data sets. And then the second is a coordinated IDA of separate accelerated longitudinal panels using cognitive function as the outcome. So I'll look at the first study of life course trajectories of BMI. So this table summarizes the age coverage and overlaps by study membership from AdHealth, MIDAS, ACL, and HRS. The full age range we have been able to study. BMI expands from 11, 12, all the way to the end of life. And the table below shows the individual and pool data set characteristics of these data, and then you can see the combined sample size, total observations, length of follow-up, and number of study waves. So this is a sort of a mega pooled study of BMI. And here's the summary data of the mean BMIs by age and birth cohort in the pooled data from 1980s to early to 2012. And here, what's highlighted in yellow are overweight. So the vast majority of these cells indicate overweight status, and those in red indicate obese. So this is the mean BMI of the US population, right? Fitting the growth curve models, we first test intra-cohort change hypothesis, where we see clear evidence of that, more recent cohorts are more obese, as indicated by higher mean BMI, as well as steeper rates of increase with age across, successive cohorts. And then we test intra-cohort heterogeneity by race and SES disparities here. So controlling for cohort, we found significant and large race gaps, especially for Blacks and Hispanics. They have huge the disadvantage early in life that dissipate a little bit in old age, and by education, also you see a clear gradient of BMI by education levels that also decrease in old age. And finally, there's also evidence for inter-cohort change and intra-cohort heterogeneity is an example of race and SES disparities. On the left, we show the race gaps in age trajectories of BMI for selected cohorts, where you see the gaps, changing with age in all sorts of different directions. There's divergence, there's parallel, there's convergence, depending on which cohorts you look at. So huge cohort variation. On the right, the mean BMI also vary a lot by parental education across cohorts, where more recent cohorts of women experience, the college-educated, women with college-educated parents experience the least cohort increases, although all cohorts increase. But there's educational differences. And so this is an example of something you could do with this sort of data. The second example is a little messier because of the very different measures across studies that we're interested in to look at cognitive function. So across the 4 studies, we have, all of them have some sort of overall cognitive assessments using different scores that encompass 2 domains. One is episodic memory, which are luckily measured the same way across 3 out of the 4 studies. ACL does not have that. The other domain of executive attention orientation function, they have some sort of overlap across studies, but not all of them are the same. So given the variety of cognitive measures across these studies, we could do 2 kinds of things. First, for the measures that overlap across these studies on episodic memory, we could harmonize the measures very easily using standardized memory scores and conduct pooled IDA just the way that we did BMI. And here's a summary of the study samples, where we have 50,000 individuals, 22 years of follow-up, and 15 waves of data. And here are the major results, where we see predicted age trajectories of episodic memory by gender, race, and education. a very, sort of curvilinear life course patterns of memory decline, and the decline began as early as late 30s and early 40s. This is a full 10 to 20 years ahead of what most of the medical interventions are starting to focus on the prevention strategies. So, and there's a race education intersection effects we found where the Black non-Hispanic males fared the worst, and then white educated, highly educated, females fared the best, and the gaps kind of are largely consistent throughout the life course with some reduction in the old age. And this is, evidence also for cohort variation in memory, where more recent cohorts, the good news is that they do better, they fare better in cognitive function, where we see higher mean cognitive function and slower rates of decline in memory. But within cohorts, we see changes in sex and race and also education disparities in more recent cohorts that these gaps are bigger than those in the earlier cohorts. So both across and within cohorts, there's differences in social disparities. The second part is the messy part where we have to deal with very different cognitive measures across all 4 studies if we are interested in overall cognitive function encompassing all the domains. And here, in this specific example, we use a simple approach of standardized test score. In more sophisticated studies, one can do factor analysis based on models. But here, just to showcase the idea, when you have very different measures across studies, it's usually the first step is to conduct a coordinated IDA of study-specific samples separately. And here is a summary of the 4 studies that have different kinds of cognitive measures, including the ACI, which was not included in the poll IDA. And here you can see, it's still pretty sizable study for each individual sample. And here are the major results of age trajectories by study. Here is we're looking at the race, ethnicity disparities across the life course. And they largely show consistent patterns with the polled IDA in memory. And they also are consistent for overlapping age ranges across these studies, although these results are based on individual studies, as you can see, and health, ACL, HRS, respectively. And we see large racial gaps that emerge very early on in adolescence that persisted throughout the adulthood. Here is the corresponding results by education. We see very much similar patterns of clear educational gradients that emerged early in life that largely persist between the highest and the lowest educated subpopulations from these studies. So there's, a ton of things you could still do even without polling the data, but having a parallel analysis of the same measures or measures operationalized the same ways using the analytic models that we introduced earlier that are sensitive to testing time-related changes. And so here are some of the key references for this, for all the examples that I have shown, as well as the project website that provide the open source codes for public access if you are to, study something else with these data sets. We don't have much time. I want to leave some time for a question at the end. So let me move on to this final couple of slides. For those of you who have come across this sort of APC analysis before, you may have noticed that it's worth noting that APC approaches are hotly debated within at least sociology and demography. It's almost like a minefield. So there have been critiques of new methods introduced here, such as Intrinsic Estimator or APC-CCREM. The problems with these critiques, I have summarized some of the points that when I came across these critiques, is that most of them, unfortunately, are very misleading for users. because the way that they have presented the problem, are largely misunderstanding or simply mischaracterization of how these new methods came about, and oftentimes rely on a lot of abuse of model assumptions and applications, in which case that one should never apply a full APC model when not all three factors are necessary, for example. So so that's sort of, the first problem with these critiques. The second is that oftentimes when they showcase something is wrong or does not work, they use examples based on simulations instead of mathematical proof. This is probably, more for serious methodologists to debate, but I oftentimes learn in my early times of studies of any statistical methods is that simulations you can come up with, it's arbitrary based on, whatever goal you set, it's arbitrary, and in order to be serious, you need to use mathematical proof. The third problem is that these critiques are still largely hinged on linear models. They're confined to linear models and aggregate data of the very first research design that we just talked about today, with no additional covariates. So they're very limited in the range of application, and yet they purported to those models to be the only model available in the universe. So that's a major problem. And accordingly, they're not very theory-driven, no intent of testing for mechanistic hypotheses, nor are they constructive. It's easy to pick something on something without saying, how else you would want to do it. How can you improve it, or proposal of alternatives. So these points are, available in these additional, publications in responses that reflect upon, these sort of discussions. So what do you do as the users, as researchers who are interested in analyzing your data and make something out of it? So I find it important to leave researchers with a unifying message that plays on the words of Box. All models are wrong, but some can be useful. And I add, some can provide complementary information we use together if you're humble enough to, want to, put everything out on the table and compare and be rigorous. So that can be done. And so I like to make calls for researchers to work together to advance the methods used in APC-related investigations, to challenge the overarching assumption today that there's a single model, a single method for APC analysis in totality, and consider multiple methods applied to the same data for model validation and a more comprehensive study, oftentimes involving multiple methods and multiple data. So how do you then select among different analytic tools? My general recommendation is that your decision should be guided by theory, measures, your data, the data structure, and the assumptions you're willing to make and inferences you're willing to draw. And then the specific guidelines, are the slides in all 4 parts of this workshop. I hope you would find them useful. And I'm always available to, take questions as, you venture into this somewhat strange field. And then, can have more discussions later on. I think we've made it in time. So now is the time for more questions, either for this section or for the overall.
I have some from online. I think there's 3 right now.
Mm-hmm.
I'll take them sort of like in order to proximity to your content. Within research design 4, does it have to have age homogeneity birth cohort that can be pooled or coordinated, or can you also include panel studies with varying birth dates? And is this possible, or is there some reason not to do this?
So theoretically, you can pull any study that followed the research design 3. If you have more than 3 studies to combine, and one of them has a single cohort, You can also combine the three because that, the other two studies will supply additional birth cohorts to overlap with that one cohort, single cohort study of one of the three studies. So if you have only two studies to combine, they somehow need to follow this kind of data structure as I show in this slide, such that you could do some sort of, combination in this shape. Does that answer the question?
I think so. I mean, I'll let this person follow up if they want to.
Hi there, can you hear me?
Oh, go
That's
ahead.
my question. Just say thank you very much for answering it. And I think, yes, you've answered it correctly. You've answered it for me to make sense, which is if I have, say, multiple cohorts, 3, 4, or 5 of them, and they're all covering it's the age range that they're covering that's the problem here. Like if there's gaps between them, it becomes an issue. But if it's the gray bit in this slide that you're talking about, the increased N within cells. So that needs to have the overlap, I presume. So say I've got 4 birth cohorts where they're like born in 58, 70, millennium cohort, etc. But then I want to substitute some of the older attrition with, say, the English longitudinal study of aging, for example. Would that be, I was just wondering if that sort of goes against, if that sort of contravenes being able to do these models with the random effect, including the cohort and the period part. But what I think you've addressed is it should be fine when you have more cohorts available. That if you have one cohort that's a birth cohort like age homogeneous and one that's age heterogeneous, then not great. That's probably not a good way of amalgamating. If that's how I've understood your response, if that's okay.
Correct. You're correct. In practice, it's much messier than this, clean example that I gave. Right? So essentially, the principle is that you can combine these cohort studies should they overlap, in age to whatever degree. They can not be completely, sort of separated so one is early life, that stop at age 20. The other is, starting at age 50. So we might have a little problem there. But so long as they overlap a little bit in age, you can use this synthesized cohort sequential design to stitch them together, and then do more than what you could do with individual studies.
Brilliant.
On the other hand, if you do have samples that don't overlap in age range or not heterogeneous in one of many existing studies that you want to combine, you could do the coordinated IDA where you fit the similar models to all these analysis to the extent that each individual can allow, and then compare the results in a parallel fashion, in a coordinated fashion, that you could still learn quite a bit. Say how, say for instance, the same associations would manifest differently across different life course stages. Right. You could somehow get some qualitative understanding of that, in ways that enhance the ability of each individual study, compared to those studies. So you can still gain quite a bit. So it's a flexible form of application you could do.
Yeah, it's really, really excellent. Thank you so much for a wonderful workshop as well. You sort of hammered home the point that it's more than the sum of its parts. That's kind of what's brilliant about the IDA, is that it allows you to go beyond what one study's doing. Thank you very much.
Thank you very much for your feedback and great question.
There's a next one here from Chang Yu, which is quite long. I'm gonna probably table this one. If this person's listening, you might want to unmute at some point. Let me just send us a message if and when you're ready to unmute. So we'll just skip that one for now and come back to that one later. The next one, for the models from part 3, is there a way to account for change in the wording of a survey question that occurred at a certain point in time? For example, could you include a dummy variable for year less than 1990, or sorry, greater than 1990 if the survey question changed in 1990, for example?
Yes, I think so. Yeah. Well, you'll have to somewhat, make decisions of the longitudinal harmonization. You can put them in a model as one variable, but it oftentimes happens in longitudinal surveys that the questions would change over time. I hate to deal with this issue because it's somehow unrelated to the topic of the modeling that I'm introducing. It's in an intrinsic measurement issue, but my experience is there are some excellent data sources that have already done the hard work for you. Try to leverage them as much as you can. So like say the RAND, version of HRS have done a lot of longitudinal harmonization, including the cognitive outcomes that I just used here. So just leverage that instead of, having to reinvent the wheel yourself. Yeah, thanks for the question.
Next one I can answer. Will this workshop be uploaded to YouTube? Short answer, yes, it will. It takes us about 30 days to process it. So we put a raw version on our website, like probably by the end of the week, within a few days. And then it takes us a few weeks to get it processed and up to YouTube. So short answer is check our website within probably like Friday or maybe Monday. And then for those that come in like next month, YouTube is the best place to go. Question back to Claire. For people who only took this workshop, what do you think is the mistake that they would most likely make and therefore should be extra careful about making?
That's a great question, actually. I think the greatest takeaway is that you should be very careful. I think here's my last slide. That's why I said I leave the best to last. Is that there's no broad, one for all kind of, solution to all the kinds of data and all the kinds of questions out there, but you should be highly sensitive to the kind of data you have and the best model that can be used to fit the data. That's why I separated out parts 1, 2, 3, and 4 carefully to kind of curate, help you curate the kinds of tools to use for the specific data you have. Some problems that the previous critiques or dissatisfaction with the APC analysis occur because of the fact that they made assumption that there's only one model, one kind of data for APC analysis, and they mistake so they kind of mismatch the model to the data structure, and that's not optimal. So I would hope that I have at least sensitized you to carefully think about what are your measures, what are your data like, and therefore pick the corresponding model to fit the data you have, and that'll avoid a lot of the headaches that you would have, if you just, use a blanket kind of approach, most often linear models to fit any data that you have. So I would say that's my best recommendation for you at the high level, but I think in this case, devils are also in the details. So I would say, if you know what data you have, it's, what research design that you're interested in, go into the corresponding section of this workshop and drill, and use the key references that I provided in the back to look at more, in-depth and extensions of these methods to understand, more, kind of, how to actually apply them and what they mean, in your own research.
I think we've got 2 more online. What do you think about Fossey and Winship's 2D APC bounding approach? Hopefully that sounds familiar to you.
Yeah.
And then instead of point identification of APC effects.
Yeah, it is a very interesting alternative. I appreciate, their perspective a lot. I think it's very complementary and help us, look at the same kind of data in different ways. There is more causal inference, based kind of approach. I appreciate it. I think it has a lot of good things about it. I do not think of it as, you have to use one versus the other kind of approach. You have to pick who is right, who is wrong. I'm, like I said, I'm against that kind of approach, and because I simply do not believe that there's one single best model for APC analysis, in totality. So, I'm very open-minded with regard to their, potential critique about the way they're not critiquing any particular specific new method talked about here. I think they're challenging the original formulation of APC linear models to social science data, which I think is, very well justified. Yeah.
Thank you for that one. Next one. I'm planning to do a project on Bayesian age period cohort model on TB data. Could you share some resources in this area?
Wow, this is a good one. TB data, the only TB data I came across was the earliest epidemiologist research that discovered the early life importance on the disease by Frost of 1939. But that was way back when. I have not dealt with TB data, beyond that literature. So I'm sorry, I don't know of any specific resource. But if you are, the question, if you already have explored some potential data set, and if I can help you find out which research design that data set belong, and then you may have some specific solution applications in mind. I haven't dealt with that kind of data myself.
Great. So we're just down to this last one. This one's from Chang Yu. Chang, I see you're still online. I'm gonna ask you to unmute right now. Hopefully this is okay with you. Feel free to speak. Let's just give you a couple minutes to speak if you're ready.
Okay, so thank you, Dr. Yang. Thanks for introducing such an important methodological approach, the longitudinal IDA approach. And data harmonization plays a key role in realizing the longitudinal IDA. And I noted that in your longitudinal IDA study published last year, you applied Z-score to harmonize cognitive function measures across datasets. However, this approach might overlook differences in the measurement atoms and demographic characteristics across studies, which could introduce a measurement error when integrating or comparing data. So I read some recent literature in epidemiology, and they tend to use confirmatory factor analysis to harmonize these cognitive measures. So given the data structure you worked with, do you think the CFA could be applied for harmonization in your context? Or what kind of challenges you think we need to address to apply this the CFA approach in harmonization? Thanks.
Yes, excellent. I love the question because it's something I've struggled in the substantive research in the application of this. First and foremost, CFA's preferred approach for data harmonization, period. Z-scores, standardized scores are useful when, especially in the case when, it's relatively simple measures you're dealing with, same tests across studies. And so the assumption of standardization is that the construct being measured is the same, is shared across studies. And then this, assumption can be violated in various, situations such as, the problems you mentioned in the epidemiology studies where they end up using confirmatory factor analysis and more, sophisticated item response models as well, that have been applied for neurocognitive tests in the past. So all these are preferred approaches for, rigorous harmonization of measures, of different measures across studies. In the examples that I mentioned in the publication, that was the very first take of social science, social surveys, cognitive measures, the first time analyzed by us social scientists. So I just did a first stab at that to sort of get, this is an initial study. It's by far not perfect. And I have actually repeatedly talked about the importance of using factor analysis in the future for better, adjustment of potential measurement errors due to unshared factor and clustering structure across studies. They're ongoing, so if you are also interested in this area, I encourage you to definitely go in that direction. And then just, so it will just move us to the next level. It does not, actually is very well incorporated, if not, implicit in the IDA framework. It does not conflict with the choice of measurement harmonization. It is kind of, the work that needs to be done within the IDA framework. So there's no, accommodation kind of issues there. So it's kind of inherent in the IDA principle of, make sure the measures are actually comparable. I hope I have answered that question completely.
Yeah, thank you. Thank you.
And then one more has come in as well. I think this is going to be the last one. I mean, up till now, I should say. How could we treat with survey weights in the polled IDA case? Can we also adjust survey weights given these weights are study specific?
Great question. You read my mind. So this goes into adjusting the principle of adjusting for study heterogeneity based on sample design. So our team have started to explore ways to compute weight for the polled data set based on the sample specific weights. It's still in progress. It's very complicated because these studies are all longitudinal. If they are cross-sectional studies, then the polled weights can be relatively straightforwardly computed, and I think it was already done in some earlier studies, I think published by UCLA in the collections of repeated cross-sectional survey data. For longitudinal studies, it's more cumbersome, and ideally, one would compute one for the pooled data set. In the existing studies that I just showed that have been published, we did not use weights in regression models, only for descriptive analysis, not for the pooled sample, but for a study-specific sample. The reason being that it's I think also sort of a known I would say fact, but opinion, that when regressions control for variables that were used to derive the weights, that tend to affect or negatively affect the estimate of the standard errors. So it's sometimes more ideal in actual regression models to not include weight for that purpose. I think the best way is to compare the models with weights and without weights for sensitivity analysis if weights are available. But so far I have not applied weights because the pooled weights have not been constructed. But comparing results with using the pooled sample without weights with individual or coordinated IDA of separate study samples applying weights, the results are qualitatively highly consistent. So I do not have strong reasons to believe the omission of a weight that needs to be computed for the pooled sample has substantially impacted the findings of these specific studies. But that's just empirical. So I would still encourage those of you who are survey methodologists to come up with ways to compute the pooled sample weights. I think it will be a great methodology paper. If I'm not part of it, I would want to be a user of the methods. It's just not being quite developed yet.
The chat is clear. Anyone here in the room have anything? Okay. I think we can adjourn here then unless there's anything else. So let's give our speaker a round of applause.
Thank you all so very much. I enjoyed all of you here today.
Yeah, thanks everybody for coming. I really appreciate your interest, and especially those that came in person. I know it's not easy sometimes, so I appreciate you, and it makes it better for all of us and our presenters, so that is much appreciated.
Thank you. Thank you for making some of my work easier by, I can walk to the screen and point things out. I missed that. I guarantee you, after the pandemic, things are not the same, but have a great rest of the day. Welcome.